Welcome to this video lecture on the topic of the design of experiments. Now, the purpose of an experiment is to discover information. In general, an experiment investigates whether there's a relationship between a factor and a response. The response is the thing we're interested in, the thing that we measure, and the factor is the thing we change to see if it will have an impact on what we're measuring. For example, we'll discuss here an experiment to investigate the effect of player on distance that a football is kicked. The response is the distance that the football travels. That's what we're interested in. The factor is the player. We will change the player and see, does that make a difference? Every experiment is like this. Experiments in medicine or in business can explore whether different strategies will affect the outcome, will bring about higher revenues or better recovery rates or something else that's of interest to us. So in general, a single factor experiment explores a single factor. In our story, it's the player, and sees how that factor impacts the response, the outcome, the thing that we measure. Now, an experiment is not the same as an observational study. We could just go to a football game as spectators and watch and see what happens. And we might notice that the goalkeeper kicks the ball further than any other player. But that might be because the goalkeeper gets a different opportunity compared to the other players when the goalkeeper kicks the ball. That's not a true guide to causes. A designed experiment helps us to identify causes because it will give every player a similar opportunity. So an experiment is a planned activity so that we can gather information about causes in a way that we can be confident about. There's a number of principles of experimental design. And the first one is this: replication. Whatever you measure, you must measure more than once. So each player will kick the ball more than once. Why is this? We want to see how big are the differences between the distances when the same player kicks the ball. That's due to random variation. There are a multitude of small things that might affect the distance, so that when the same player kicks the ball repeatedly, the distances are not exactly the same. We need to measure how big those differences is, because that's the random variation. When we've measured the random variation, then we're in a position to see if one player is different from another player, and if it didn't just happen due to random chance. But we must measure random variation, and we do that by replication. So whatever factor level we choose, we replicate that factor level a number of times, and we do that for every factor level. The factor levels in this story are the different players. So first principle, replication. You must measure everything more than once. The second principle of experimental design is randomization. We don't allow one player to take all of their kicks at the start of the day and then move on to the next player and then move on to the next player, because later on weather conditions or something else may give rise to conditions later on that are more favourable for kicking the ball a long distance. And so we will be mixing up the effect of the weather with the effect of the player. So anything could be related to time. So as time passes, we don't want all of one player's kicks to happen later or earlier. So we randomize the run order. We make a list of all the kicks that are to be performed. Each kick is called a run, each single observation in an experiment. And then we use random numbers to determine who goes first, who goes second, who goes third. That way there is no particular pattern in the occasions when each player kicks the ball. And so that if there is some pattern in the weather or in some other environmental variable, that will not impact the results negatively for one player. We're talking here about randomizing the run order, but sometimes we need to randomize the allocation. Suppose we have two different drugs that we want to compare, and we have a number of patients or subjects to whom we will administer these drugs. We randomize the allocation of the drugs to the patients, rather than giving drug one to the first patients who show up, who might be healthier or who might have been sick for longer. Instead, we randomize the allocation. So where there are experimental units, like patients, something on which the test will be carried out, we randomize the allocation of the experimental units to the different factor levels. A third way in which we might use randomization would be random selection. Let's say we want to compare tablets in two different batches. We've manufactured two batches of tablets. We want to compare the weights to see, does the factor batch affect the weight of the tablet? We would randomly select some tablets from batch 1 and randomly select some tablets from batch 2 so that the selected tablets will properly represent the batches from which they came. A non-random selection, we can't be sure what that's going to tell us about the batch. So randomization is important in experiments, and it could mean randomizing the run order. It could mean randomizing the allocation of the experimental units to the factor levels, or it could mean randomizing the selection of items that we take. Now, when we carry out the experiment, the big question is, does the factor affect the response? So in our ball kicking experiment, we are interested to know if the distance that the ball travels depends on the player who kicks the ball. When the ball is kicked, it travels a certain distance, which is the average distance it travels for any player, which we might call mu. Plus, it may travel an extra distance because of that particular player. We call that alpha. So the average for an individual player is mu plus alpha for that player. And then, of course, on each individual occasion, it may travel further than that, or not as far as that. So there's also a random element, epsilon. So the total distance travelled by the ball on a single occasion is mu, how far the ball would travel on average for anyone kicking the ball, plus alpha, how much further on average the ball would travel when that player kicks it, plus epsilon, the error. Now, the null hypothesis that we test is that the player has no effect on the distance, which is like saying that all of the alphas are 0. So when we study the data, the question is, are there differences between players that cannot be explained by random variation? Are the differences between the players so great that we can say this did not happen by chance? So we calculate the variance between the players. And we also calculate the variance within the players. The variance within is the random variation. It's the variance that arises when you don't change the player. And then we ask the question, is the variance between significantly bigger than the variance within? So we're looking at the explained variation that's caused by a player. We're looking at the unexplained variation that happens even when it's the same player. And we're asking, is the difference so big that we must conclude that the players are different? We do this analysis using analysis of variance, or the acronym is ANOVA, A-N-O-V-A, analysis of variance. And so in an ANOVA table, we look at the variance ratio. It's the ratio of the explained variation to the unexplained variation. And that gives us an F statistic and a p-value. And if the p-value falls below 5%, then we reject the null hypothesis and say the factor has an effect on the response. The assumptions that we rely on when we perform an ANOVA are, first of all, an important assumption, that is, that the errors are independent. The experiment is free from systematic bias, so there is no tendency for one player to provide kicks on every occasion that are better than the average for that player. So if the experiment is well planned and randomized, then it should be free from systematic bias. And so even if one player on one occasion gives a kick which is better than their average, we don't expect that they will do that every time. So the errors are independent. And that's an important assumption, that the experiment is free from systematic bias. If there's systematic bias in the experiment, there's no point analyzing the data at all. We have a flawed experiment there. Two other assumptions are of a mathematical nature. The second assumption says that the errors are normally distributed. So when a player kicks the ball travels some average distance. Sometimes it goes a little bit further, sometimes not as far as that. Most of the time it travels a distance that's close to the average of that player. So we get our familiar bell-shaped curve. And so for every player who kicks the ball, that's the outcome. And so the errors in the experiment are normally distributed. The third assumption that we make when we're analysing the data from experiments is that the variances are equal. So even if one player kicks the ball further than some other player, we're assuming that the spread of the distances for one player is the same as the spread of the distances for every other player. We're assuming that the variances are equal, even if the means are not equal. That's a simplifying assumption, which we often make. In fact, the second and third assumptions, the normality and equal variance, those assumptions, even if they're not perfectly satisfied, our analysis technique, ANOVA, still works well. But the first assumption is essential. The experiment must be free from systematic bias. But we say that ANOVA is robust, so that even if there is some mild non-normality or some inhomogeneity of variance, then ANOVA can still be used to provide a verdict on the data. You can read more about this in section 7a of the textbook.